Thank you very much for coming today. I'll be presenting with spreadsheet for the first time. It's this really fancy presentation tool. Wow. Yeah, you can click, you can zoom in, zoom out. But that's not the important part. The important part is I'll be talking about my summer internship project from this past summer with Sanofi Pasteur. So, too far. Right, introduction. We'll be looking at pneumonia outcome, flu vaccine, and other lung or throat pathogens and see how these three relate. The motivation for doing this is pneumonia is quite serious in older adults, 65 years or more. It's the third leading cause of hospitalization and the sixth leading cause of death. And flu, we care about flu pretty much because Sanofi makes flu vaccine. So we care about keeping people free from flu and making money. From this very particular study that I'm not allowed to talk about, they found out that flu vaccine might affect pneumonia by some other means other than through flu itself, like by other pathogens that we mentioned. So from this study, we're gonna do a post hoc study of it. We select a sample, we subsample who consent to have their samples used for future study. We picked everyone who had pneumonia. We picked a random samples of those who did not have pneumonia. And they're still doing lab tests on that. The results would come in at the end of the year or early next year. So I actually haven't seen the data yet. I'm expecting to see flu vaccine treatment, which is categorical whether they have the flu shot or not, or if they have placebo, or so on. I'm expecting to see pneumonia outcome, which is categorical whether they have pneumonia or not, and I'm expecting to see other pathogens, which will be continuous in colony forming unit. So from this data, my boss wants to figure out if other pathogens mediate the effect or not, the effect of flu shot. Does everyone know what mediation is? I guess not. Mediation is pretty much, say, the treatment is the department gives you a raise. The mediation might be something like, I'm going to spend this money on food, and food makes me happy. So the effect goes from money to food to making me happy. So food mediates the effect of getting a raise in this case. Anyway, so if the pathogens do mediate the effect, then he also wants to know which one. From that, the model I'm thinking about is multivariate mediation with multinomial outcome, well, binomial, but it can be extended to multinomial outcome. Visualizing the model, X would be the treatment, either flu shot or not. M is the mediators, so M1 might be pathogen 1, flu, M2 might be pathogen 2, rhinovirus, and so on. And it's quite reasonable to assume that these pathogens are correlated. And Y here is the pneumonia outcome. So the main problem in this analysis is the correlation between the mediators. So it would be nice if there's some way to get rid of it. A few years ago, 1 or 2, Dr. Lindquist from Johns Hopkins came and gave a talk about pretty much this, but he has continuous outcome. So the model is, so the plan is to transform all these N's using a matrix W so that the outcome is uncorrelated. So it's a lot like, it should remind you of PCA, principal component analysis. But instead of transforming it so that it explains the most variance, we're transforming it so that it explains the most likelihood, or it's maximizing likelihood. And it's just fitting linear model with variance assumed to be known. I'll pause right here a little bit. Does anyone have a question about this slide? All right, moving on.
I'll ask, yeah.
Yeah.
Does this transformation affect interpretability at all? I mean, interpretability, that's the word.
Interpretability of...
Is it still easy to understand the results of any inference after you do the transformation?
Yeah.
Okay.
The transformation is actually answering the main questions that we are wondering about. So if W is significantly different from 0 then that's telling us that the non-zeros entries in that W means that correspond to the M intermultiplication. So those variables would be important. So those variables would mediate the effect.
Gotcha. Okay.
Yeah. All right, moving on. So I thought, yeah, we might as well do the same thing. We just change the Y model from continuous to logistic regression like we used to. But the problem is, going back, optimizing this objective function with that constraint is pretty easy because that's quadratic in the parameters, and the constraint is also quadratic. We take derivative, it's linear, we can set it to 0 and solve. But changing from quadratic to logistic is a lot harder because derivative cannot be solved. Setting derivative to 0 cannot be solved. So it's not easy. Does anyone have a question about this slide? All right, moving on. So I'll talk about the optimization strategy that I spent the most of the summer on. So just looking at this optimization problem, first thing I noticed is holding all the other parameters constant. If you look at alpha, it's convex in alpha. And we can solve it quite easily using least squares. So optimizing with respect to alpha is no problem. Looking at beta, it's also convex in beta because that's pretty much a softmax function which is convex in beta. So it is convex. So we could solve that using logistic regression. Looking at W, it is non-convex because we have a non-constraint of 1. And I actually don't know how to solve this because W appears here, and in down here. So the main problem is cracking W. If we can figure that out, then we can solve the whole problem pretty much. So we know that W is in here. If we can split that out from here, it looks a lot like normal least squares. We can solve that. If you can split that W from that constraint, then we can also solve that using logistic regression. And if you can split that from that, then it looks a whole lot like ridge regression, which we also know how to solve. The problem is just it's appearing together. So we'll come back to that later. As I mentioned, it's not convex in W, but convexity is nice in many ways. Local minimum is guaranteed to be a global minimum. First order conditions imply optimality. So we would like to have convexity in here. So putting everything together, we know that alpha, optimizing with respect to alpha is very easy. So we're going to profile out alpha by doing least squares and then just plug in what alpha should be. So that's our projection matrix with 1 and x. And then we're going to relax constraint from equality to inequality. So from that equal sign, it becomes unequal sign. And then we're going to rescale beta and w so that the norm becomes 1 like we wanted, and just hope for the best. Oh, sorry. I mentioned earlier that the problem is w appears in too many places that are hard to solve together. So if we could split it, we call it variable splitting, into smaller, easier to solve problems, then we're good to go. I remember to do this because I took advanced computing with Professor Chi, Dr. Chi, from lecture 21, page 3. It says, here's the optimization problem. We have one part that's easy to solve, another part that's somewhat easy to solve, but these variables x and z have to be related somehow, linearly. For example, lasso. So thinking about that, I thought, oh yeah, that should totally work in my case. I'm going to give it a try. So back there, that's called ADMM. For those who don't know ADMM, I'm going to introduce it here. ADMM stands for alternating direction methods of multipliers. But the important part is we're going to optimize one at a time, and then we introduce this augmented part, and we use the augmented part to make sure that the constraints hold. So if the constraint holds, that part goes away. So it's the same problem. To solve the augmented Lagrangian, we can use gradient descent. But the problem with that gradient descent is optimizing both x and z together could be hard, like in our case. So we just split it into two, optimizing f with that part, optimize g with that part, and use that part to make sure that x and z are consistent. That's pretty much ADMM. And there's that part that shows up from the Lagrangian. It's not too bad, but we could absorb that into the quadratic term by completing the squares. So in the end, that's what we had to do. Going back to our problem, that's the Lagrangian. We have the negative log likelihood part that we would like to minimize. We have norm 1 constraint, and we have the ADMM augmented part. So the f is the negative likelihood, the g is the norm constraint. So doing it this way, we can separate the likelihood part and the constraint part, both of which we know how to solve separately. And we just link the two using the ADMM augmentation that I mentioned. So solving the f part, we could use BFGS. BFGS is like, is a lot like Newton's method. I'll leave the details out a little bit. But the gist of it is it's easy to do. That update is also easy to do because it's quadratic. Take derivatives, that's linear, set it to 0, we can solve that. And the U update is straightforward, like, like here. After we know the new x, after we know the new z, we just type in the update. So knowing that I could actually solve this problem, but I do not have the data to do it. I conducted a simulation study to see what I would get to see if the method holds or not. So the setup of the simulation is I use Gaussian cupola, which is a fancy way of specifying joint distribution of m and x. So I get distribution of x, the treatment. I say it's binomial with probability a half, and I have conditional probability or conditional distribution of the mediators and x. Then I specify the true W and the true beta. From there, I can compute the probability which width I could use to draw y, the response. In each iteration, I have 500 sample size, and the ADMM parameter is set to 2, and I tried a couple different values of variance with the same starting values of each parameter. Anyway, the result looks quite promising. The true value is on the rightmost column. The mean is right here. That's the confidence interval. So it looks like it's centered around the truth with reasonable spread. W doesn't seem to be affected by my choice of sigma squared very much. Beta, on the other hand, the beta estimates do get spread out more as sigma squared goes higher and higher. I'll leave this up for a little bit if you want to take a look. And we see the same thing for higher values of sigma squared too. So to wrap it up, since we are interested in the W vector, and it's quite robust to choice of the hyperparameter, I think this method holds quite well. There's a speed and precision trade-off, but if you have a really good computer, then it doesn't really matter that much. To sum everything up, convexity is nice and you should try to get it in your problem if you could. If you have a problem that's hard to solve, you can use ADMM to split it up into smaller, easier to solve problems. Spreadsheet which I'm using looks fancy, but it's not very good for mathematical presentation. You should go get your flu shot, and you should take advanced computing to actually understand what I was talking about. Do you have any questions? Yeah.
So I haven't taken advanced computing. I will take it in the spring already, signed up. But how do you set that rho value for the ADMM?
Very good question, thank you. Rho is typically chosen to be somewhere between 1 and 2.5. It doesn't really affect the estimate, it affects convergence rate.
Okay.
So,
that makes sense, I think.
Yeah, so I kind of arbitrarily chose it to be 2.
Right. And then second question, given your problem, do you have any idea why those betas are more sensitive to the changes in variance?
I thought about it, but I'm not sure if I get it right. So that's sigma squared. It behaves like variance.
Oh yeah, I guess it's not necessarily variance, right? It's kind of scaling parameter.
Yeah, well, from the model, we say this epsilon follows normal with...
Right, okay, got it.
Yeah, with variance sigma squared, and I just treated sigma squared instead of another parameter to estimate. I said it's a hyperparameter that we can actually plug in. So it should look a whole lot like variance. So the higher sigma squared is, it's reasonable to assume that we would have larger confidence interval.
Right.
But I actually don't know why that affects only beta but not W.
That's kind of an interesting thing to think about, like, especially when you actually get the data. Like, I forget what beta is, but it's like, why is this beta more affected by the variance in the data?
Mm-hmm.
Yeah. Very cool. Well, thank you.
Yeah. If you want to know more about ADMM, there's that paper that's really good. It goes into great details about it. I think it also talks about choosing the hyperparameter to get the optimal convergence rate, but that's quite dependent on the f and g functions. All right, short talk. Thank you, Pat.
Thank you, Pat.
Thank you for coming.